Hi, this is Wendy Lightheart, and in this video we're going to be learning about compound inequalities. First, we're going to learn about the concepts of intersection and union. When the word "and" or the word "or" is used to connect pairs of inequalities, we call the statement a compound inequality. To solve compound inequalities, we need to know how to find the intersection and union of two sets. The intersection of set A and set B, written as A and then a symbol that looks like an upside down U, and then B, is the set of all elements that sets A and B have in common. Sometimes we like to think of that as the overlap. So the elements that they share, if we collect all of those together, that would be considered the intersection of those two sets. The union of set A and set B, written as A and then what looks like a U symbol, and B, is the set of elements that belong to set A or belong to set B, or they might belong to both. So any of the elements that belong in either A or B or both, take all of those elements together and you will have the union of set A and set B. Sometimes we use Venn diagrams to illustrate what the intersection and union of sets look like. So if you look at the area in purple in figure A here on the left, the purple area, the overlap, represents the intersection of A and B. And then if you look at the figure on the right, figure B, the area shown in both shades of pink, so all of A and all of B together, including what's considered the overlap, all of that pink area together would be considered the union of A and B. So let's look at an example just looking at some basic sets made up of a list of numbers. So we're going to let A be the set of 0 through 6, those integers, and then B is going to be the collection of integers -4, -2, 0, 2, and 4. And we're going to find both the intersection, which is what's being asked in part A, and the union of those two sets. Since 0, 2, and 4 are common to both sets A and B, and remember that the intersection is the collection of all the elements that they both have in common, so 0, 2, and 4 are common to both those sets, which means the intersection of A and B is the set that includes those three numbers, 0, 2, and 4. Then for part B, we want to find the union. So we're looking for all numbers that are in either or both sets. So we would list, if we list them in order, from smallest to largest, we'd have -4 is in set B, -2 is also in set B, 0 is in both, 1 is in set A, 2 is in both, 3 is in set A, 4 is in both, 5 is in set A, and 6 is in set A. And notice that we have listed all the elements that are either in A or in B, and then also including the ones that are in B, or in both of them as well. And this is the set that we obtained. So this is the union of A and B. And note that those numbers that they have in common, the 0, 2, and 4, even though they're both in sets A and set B, we're only going to list them once when we list all those elements that are in the union. Okay, so let's start talking about solving compound inequalities now. So we're going to solve this compound inequality. And remember, a compound inequality is just two compound inequalities that are combined with the word and or the word or. So this one's combined with, these two are combined with the word and. What we want to do is we're going to solve this compound inequality, which technically this one's already solved, and then we're going to graph each of these solution sets to find the solution set for the compound inequality. And then we're going to learn how to give the solution set in interval notation. So if we look at the first inequality, x is less than 1, recall that to graph that, we're going to have a parenthesis at 1 since we're not including that number. And we want to include all the numbers that are less than 1, so we have an arrow pointing to the left. So that's the graph of the first inequality. Now we'll graph the second inequality, and this time we want numbers bigger than -3, so we're going to go to have an arrow going to the left to include all numbers that are bigger than -3, and a bracket because we are including the -3 since we're looking at all x's that are greater than or equal to -3. And also notice that I've lined up my numbers, so if you count these hash marks here starting at -3 and move to the right, -3, -2, -1, 0, and 1, you'll see that the 1 on that graph lines up with the one on the one above. So this is really the way you want to do this so that you can see the intersection. So what I like to do is think of well, I'm looking for the overlap of these two, right? That's what the intersection is. So I like to think of picking up one graph and setting it on top of the other one and seeing where these two arrows are overlapping. So let's see how that works. We're picking up the bottom one, laying it on top of the top one, and then notice this area between the -3 and the 1 is the overlap. Those are all the x's that are both less than 1 and at the same time greater than or equal to -3. So that's considered the intersection of those two solution sets. Now to write that in interval notation, our smallest number in that range there is -3, so we're going to start that with -3 with a bracket, and then a comma, and then our largest number in that set would be 1, but we're not including 1, so we're going to put a parenthesis after the number 1. And that is our solution in interval notation. Okay, let's look at another one. This one, now we're going to have to actually solve this inequality, because you'll notice that the x's are not isolated in this example. So we're going to solve the inequality, and then we're going to do just like we did with the last example. We're going to graph each solution set individually, and then we will look at the overlap to find the intersection of these two. So if we solve the first inequality, the only thing we have to do really to isolate the x in this inequality is to add 5 to both sides. So if you add 5 to both sides, you will obtain x is less than or equal to 8. So the first inequality is now solved. Now let's look at the second inequality. This one we're going to need a couple steps. We're going to need to subtract 3 from both sides first. That will give us 4x is greater than -4. And then if we divide both sides by 4, we'll have x is greater than -1. So now we have those two inequalities. The first one we ended up with x is less than or equal to 8, and the second one gave us x is greater than -1. So remember, we're looking for all x's that are less than or equal to 8 and at the same time greater than -1. So that would be the intersection. Just remember that and always denotes the intersection. So let's look at the graphs of these two. So the graph of x is less than or equal to 8 would start at 8 and then have an arrow pointing to the left, indicating all x's that are less than 8. And we will have a square bracket there because we are including the number 8. Then for x is greater than -1, we're going to have a parenthesis at -1. And you'll notice that this is 9 units to the left of 8, so that they're lining up. And then we have an arrow pointing to the right because we want all x's that are greater than -1. Now if we pick up the bottom graph and lay it on top of the top one, we will be able to see the overlap. So this is something you can just do mentally in your head and kind of look at where these two graphs are overlapping. So notice they're overlapping from -1 but not including -1 because -1 is not in both of these sets, it's only in one of them. And then it goes all the way up to 8, and it also includes the number 8 because 8 is in both of these solution sets. So interval notation would be parenthesis, -1, comma, 8, and then a square bracket after the number 8. Okay? All right, so let's look at another example. This is considered a compound inequality. If we were to read this just from left to right, it says 25 is less than or equal to 6x plus 4, which is less than 49. Now we could rewrite this into two inequalities separated by the word and, like so. Because this says that 25 is less than or equal to 6x plus 4, but it also says that 6x plus 4 is less than 49. So we could split it up like that with the word and then we'd know this is an intersection. We could solve each of them individually, graph them each separately, and go from there. But in this case, because of the way this is written, it's actually easier. There's an easier way to solve the compound inequality instead of separating it out like that. So let's see how we would approach a compound inequality that's written in this form. So what we do is we want to isolate the x in the center. So usually we're isolating a variable on the left or right of an equal sign or less than or equal to sign or greater than sign. However, here we have two inequality signs. So what we want to do here is we want to isolate x in the center. And the way we do that is very similar to how we isolate an x in an equation or a regular inequality. Except for instead of doing the same thing to both sides, here we actually have three sides to consider. We have the left side, the center, and the right side. So we're going to do whatever it takes to isolate the x in the center, and we just have to remember that whatever we do to the center, we have to also do to the left side and also the right side. So if we want to get x isolated in the center, we would need to subtract 4. So we subtract 4 from all three of those parts there, the left, the center, and the right. So that'll give us 21 is less than or equal to 6x, which is less than 45. Now to isolate the x in the center, we just need to divide by 6. So we divide everything by 6, all three of these. And that will give us, and if we reduce this fraction, 21/6 reduces to 7/2, which is 3.5. Since we're going to be graphing this, we'll go ahead and convert that to a mixed number. So we have 3.5 less than or equal to x less than 7.5. This is our compound inequality now solved since the x is isolated in the center. Okay, so this is what we have, and if you read this, now we're going to split this up with the word and, because what this is saying is, notice that it's, the first inequality sign is opening up to the x, so it's saying the x is bigger than 3.5, and x is at the same time less than 7.5. So now we have it written in a form that we're familiar with, and we're ready to graph the two and look for the overlap. So here's our x is greater than or equal to 3.5 graph. Notice that the bracket is placed halfway between 3 and 4. And we do have a square bracket there since we are including the number 3.5. And then for x is less than 7.5, we'll have a parenthesis because we're not including the number 7.5. A parenthesis halfway between 7 and 8, and then pointing to the left. And if we look at the overlap, looks like it's going from 3.5, including 3.5, up to 7.5, but not including 7.5. So interval notation would look like a square bracket and 3.5, which is the smaller number, comma, 7.5. And then, of course, a parenthesis at the end because we're not including 7.5 in our intersection. Okay, so now the word or, we'll look at a couple of examples with the word or. So remember, or denotes the union of two sets, and the union of two sets are all of the elements that are in one of the sets or in both of them. So let's start these off the same way that we did with the intersections, in that we're going to solve each inequality separately. Then we're going to graph the solution set for each of them. And then by looking at the graphs, we can see what the union is of those two sets. So if we solve the first inequality here, we would need to subtract 7 from both sides, and that will give us 3x is less than or equal to negative 18. Then we divide both sides by 3, which will give us x is less than or equal to negative 6. So that's our first inequality solved. Now let's look at the second inequality. To isolate the x here, we're going to need to add 3 to both sides, which will give us 7x is greater than or equal to negative 14. Then divide both sides by 7, and we obtain x is greater than or equal to negative 2. So now we have our x is less than or equal to negative 6 that we found earlier. That was our first inequality. And here is the graph of that inequality. And then the inequality x is greater than or equal to negative 2, we'll graph that solution there. And now we're looking for the union. So what we're going to do is join these two sets together. So if we add these two sets together, that will give us the union. And so since there's no overlap here and they're completely disjoint sets here, the way we would notate that is actually with a union symbol. So we'll use interval notation for each of those inequalities separately, since there is no overlap, and then simply put a union symbol between them, and that will give us all the x's that are less than negative 6 or less than or equal to negative 6, or all the x's that are greater than or equal to negative 2, which is what it was asking for in the first place. All right, let's look at one more union example. So we're going to solve each inequality separately, then we'll graph both of those inequalities, and then we're going to join those two together to give us the union of the two inequalities. So the first inequality, we would need to subtract 10 from both sides first to isolate that x. Then we would divide both sides by 5. So that gives us x is greater than or equal to 5. Okay, so now let's look at the second inequality. For this one, we could solve this by subtracting 8 from both sides, which would give us negative 4x is greater than negative 32. And now to isolate the x, we would need to divide both sides by negative 4. But remember, when you divide both sides of an inequality by a negative number, you have to flip the sign. So we'll obtain x is less than 8. So that's the solution to our second inequality. So now if we look at the two graphs, the first one, remember, was x is greater than or equal to 5. So that would be a square bracket and then an arrow pointing to the right. And then our second inequality worked out to x is less than 8. So we have a parenthesis at 8 and then an arrow pointing to the left. Now notice when we join these two together, we're going to end up with an arrow pointing to the left and to the right with no gap in there at all. So it's really going to cover every single real number that there is, all the way from negative infinity to positive infinity. So that would be the union. So really any x would be a solution to that original compound inequality that we were given with the OR. All right, so that's it for today. Keep working on those inequalities and have fun. See you later. Bye-bye.